Hello, and welcome back. Chapter 8.2, third video, molar concentration and dissolving. We'll start with the dissolving process. So, what does it mean to dissolve something? What you're doing, and this is a review of middle school where I know you learned nothing, is when we take a solvent and we dissolve it. We take a solvent and we use that to dissolve a solute. So the solvent is the thing that does the dissolving. And the solute is the thing that gets dissolved. And when we put these together, we make what's called a homogeneous solution. That means that they look like they're one entity, but they're really not. What it is just the solute has become spread out inside the solvent. So, one of the mechanisms by which to dissolve something is through what's called ionization. So what we do is we are going to bring a solute and solvent together. So we're going to pour the solute into the solvent. And then two, the particles are going to interact, what we call subvolysis. So let's say we have a sodium chloride crystal. We have a sodium ion bonded to a chloride ion, and then another sodium, and then another chloride, and then this continues until we make a three-dimensional array called a crystal lattice. And I'm only going to draw a little bit of it here. Now, water molecules are what we call polar molecules. And polar means that they have opposite ends. They have a positive end where there's a deficiency, and they have a negative end. So in the structure of H2O, the hydrogens represent the positive end, and the oxygen represents the negative end. So what happens here is that a water molecule will get in there and will attract the chloride and then pull it out. And then another water molecule, its negative end, will attract the sodium and then pull it out. So really, water has a job to do in this. As a solvent, there's a negative end and a positive end. So each water molecule can attract a chloride ion on one side and a sodium ion in another, and then separate them. So we have this particle interaction where the polar molecule dissolves the polar crystal. And then three, the particles spread out. And this spread, we're going to go into this in detail in another chapter, but when they spread out, we call this Brownian motion. So when they talk about solutions, especially in the lab, they talk about its concentration. So we're going to do two terms here: concentrated versus diluted. All right, if the solution is concentrated, then we think of it in terms of being more like the solvent. In other words, let's say you had, I hate when I do stuff like that. Oopsie poopsie. Sorry, when it's concentrated, it means it's more like the solute. And when it's diluted, it's more like the solvent. Fruit juice. If we have concentrated fruit juice, and we say concentrated, then we expect it to taste really sweet, really concentrated with that sugar. And if it's diluted, we would expect it to taste watery. So the difference between the two: concentrated fruit juice tastes more like the solute, which is the sugar, and diluted fruit juice tastes more like the solvent, makes it taste watery. So in the lab, safety has to do with the concentration of the materials that we're using. Most of the materials we're using are dissolved in water. So for the sake of this chapter, and I hate that they use this term, they call water the universal solvent. Now, water's not really a universal solvent. It is good at dissolving a lot of things. It is inexpensive, and unless you live in the desert, it is pretty easy to get a hold of. So it's safe, it's cheap, it's easy to get a hold of, and it does a pretty good job of dissolving a lot of things. Even you, if you swim, you dissolve a little bit in the water, but not much. So when we talk about safety in a lab, we talk about the concentration of the materials we're using dissolved in water. So for this chapter, we're going to assume that all of these things form what's called an aqueous solution, which means dissolved in water. Now, can you dissolve it in other things? Absolutely. You can dissolve things in oils and fats. You can dissolve things in alcohols. There are lots of things that you can dissolve stuff in, but we're going to focus on water. So when we talk about concentration, there's a lot of different ways to describe concentration. How much solute you have, how much solvent you have. One of the ways is to use density. But in our labs, we use something called molarity, and they use a capital M to represent molarity. So I'm going to write that, molarity. And the units for molarity are moles of solute divided by liters of solution. Now, one of the problems with using molarity is molarity changes based on temperature as things expand and contract. But for reactions run at room temperature, molarity is going to be our standard unit. Give you an example where this is important. If we have 12 molar hydrochloric acid, as soon as you take the lid, this is the most concentrated we can buy, as soon as you take the lid off of the jar, you start to see vapors rise up, and then you could choke and kill yourself because it's going to start to dissolve your eyes, your throat, your lungs, etc. So if it's a 12 molar solution of hydrochloric, we say it's concentrated hydrochloric, and that means that we have 12 moles of hydrogen chloride dissolved in enough water to make a 1 liter solution. Now, the reason why I don't say it's 1 liter is for two reasons. One, the hydrogen chloride takes up some of the space, but two, the actual volume of the solution depends upon how the stacking of the particles occur. Remember, I talked about stacking and density. Some solutes and solvents stack really well together, and if they stack really well, you could take a liter of solute and a liter of solvent, and you could actually get less than, oops, I used the wrong symbol. You could actually get, when they mix together, less than 2 liters of total volume. Or if they don't stack together as well, you could take 1 liter of solute, 1 liter of solvent, and get more than 2 liters of solution. So the volume has to do with the stacking. So we don't really concern ourselves with how much water. We're going to take these 12 moles of hydrogen chloride and we're going to dissolve them in enough water to make a 1 liter solution. So anytime I use 12 molar hydrochloric acid, I use it in the fume hood because I don't want to die. Now 6 molar hydrochloric acid, again 6 moles of hydrogen chloride and enough water to make 1 liter. This is the sort of thing where you can use it, but don't get close to it. It does create a little bit of acid vapor, and it's the sort of thing that it's a dehydrating agent. So if you're wearing contacts, it'll dry out your contacts and make them very difficult to remove. If you ever wore contacts, you know that sometimes the contacts stick. Take that and multiply it by 10. That's how much your contacts are going to stick around 6 molar hydrochloric. In most of the labs we do at this level, we use 0.01 molar hydrochloric acid. So 0.1 moles of hydrogen chloride in enough water to make a 1 liter solution. And that's the sort of thing that as long as you don't pour it on your skin and as long as you don't drink it, you're going to be safe. I still wouldn't put my nose next to it and try to breathe it in, however. All right, so certainly safety in the lab. We need to know the concentration of the material. So here's the format. Again, if we say that something is 0.24 molar, let's say we have iron sulfate. Again, this is read as molar, and that means we have 0.24 moles of iron sulfate dissolved in enough water to make a 1 liter solution. So that's a conversion factor. Moles over liters. In fact, we should call this liters of iron sulfate. Now, when they write this, they only include the solute. But it's actually solute plus water. But they leave the water out. The only time they include the solvent in this notation is if the solvent is different than water. All Alright, so what type of problems can they give you with this ratio? Well, it's just like anything else. If we know two of the variables, can we solve for the third? If we give you information, can you substitute it into the formula to be able to use it? So let's say we have 2.67 moles of sodium chloride, and we're going to dissolve that in 454 milliliters of, we're going to make 454 milliliters of solution. All right, so what is the molarity? What is another term for molarity? Is something called molar concentration. So what's the molar concentration of this solution? Well, it's pretty easy. We just set up our formula, do a formula-based approach. Molarity is moles divided by liters. We're going to have to convert the 454 milliliters to liters. So let's do that. 1,000 milliliters is a liter. So this comes out to be 0.454 liters. We're going to substitute that in. And they were nice enough to tell us how many moles. So we're going to do 2.67 divided by 0.454, and we get 5.881057.269. How many sig figs? Looks like 3. So we're going to do 5.88. Now you can leave it as moles per liter. I tend to like to do that, but when I'm labeling bottles, I'm just going to put capital M for molar. So 5.88 molar sodium chloride. We do not include the solvent. So number 5.88, unit, molar, chemical label, NaCl. Alright, what other problems could they give you? Well, again, we could give you two things and ask you to solve for one of the other variables. Suppose we have a 3.64 molar solution of sodium chloride, and we pour out 1.72 liters of this solution. I want to know how many moles of NaCl would we have. Alright, so again, we set up our formula based. Molarity is moles of sodium chloride over liters of solution. We're going to solve for the variable, so moles of NaCl is equal to molarity. Now at this point I'm going to convert molarity into units, moles of NaCl over liters, and then we're going to multiply that by the liters. So this is going to be our molarity rating times the liters. And of course liters cancel out and we're left with moles of sodium chloride. So let's substitute that in. So we get 3.64 molar, so moles over 1 liter. And they said let's not use a liter, let's use more than that, 1.72 liters. So we do 3.64 times 1.72, 3 sig figs, and we get 6.26 moles. Oh, I'm sorry, let's just write the answer down here. 6.26 moles of sodium chloride. Now, of course, we don't have a molometer in the lab in order to make this solution. So what is it that we're really going to be seeking here? And that's going to be grams. How many grams of sodium chloride do we weigh out? That would be a better question. So again, suppose you go into the lab and they say, hey, we want you to make 250 milliliters of a 1.2 molar solution of NaCl. How are you going to do that? Well, the first thing you have to do is you have to weigh out the solute. So we're going to ask you to do the calculation. What is the mass of NaCl needed to do this? So we can use our molarity rating, right? And we can solve for mass. So formula-based approach. Now, we don't have to do formula-based. I'm going to do this as a conversion problem. Start with what they give you. You are starting with 250 milliliters of solution. I'm going to convert that to liters because molarity is in moles per liter. Then I could just say for every 1 liter of solution, I have 1.2 moles of sodium chloride. And then I can go to the periodic table, do moles of sodium chloride and then compare it to grams. So I look up the mass of sodium chloride, and it is, oh, is it 0.443? I got to add this up again. You think I would know. 22.99 plus 35.453, 58.443. Look that up. So 250 divided by 1,000 times 1.2 times 58.443, and I get 17.5329. So I'm going to do 3 sig figs. 17.5 grams of sodium chloride. Easy, right? Of course it is. Now, can this get a little bit more complicated? Well, yeah, because everything we learned in the previous videos, we can now apply to this. So I'm going to pull a question from the slideshow. And before I do that, I should emphasize this. Let's take a look at this. One thing I skipped. In your textbook, they talk about decimeters cubed and centimeters cubed because those are the cubic meters, or decimeters cubed rather, is going to be the SI unit. However, nobody does that. Just know that 1 decimeter cubed is the same as 1 liter, and 1 cc, 1 cubic centimeter, is the same as 1 milliliter. Alright, so let's pull up that problem then. Alright, here we go. We have 0.200 liters of a 6 molar hydrochloric acid sample used to reduce copper oxide to copper. That's a lab we would do. How many grams of hydrochloric acid have reacted? Alright, that's a good question. Let's do it. Now, we don't have to understand what's going on in this reaction to be able to do the problem, because we can rely on our technique, our formula-based technique, or our conversion factor technique, whatever we decide to do. So when I look at this problem, first thing I'm going to do is ask myself, what is it that they're actually asking me to find? They're asking me to find grams of hydrochloric acid. Alright, so what do I know? I know there's a relationship between grams and moles on the periodic table. I know there's a relationship between molarity, because molarity is molarity is moles divided by liters. So I have this information I can use. So I'm going to start with what they give me. Now the question is, do they physically give you 0.2 liters of solution, or do they physically give you a 6 molar rating? And that's hard to determine, but it's actually the rating that is consistent throughout. So the thing I'm going to focus on here is how much of that material they gave us. So I'm going to start with that. I'm going to start with 0.200 liters of HCl. And according to the molarity, I know that 1 liter of HCl is going to give me 6.0 moles of HCl. And now they want to know how many grams of that. So I can go to the periodic table. 1 mole of HCl. I can look up hydrogen, which is 1.008, and add it to chlorine, which is 35.453. And that comes out to be 36.461 grams. Alright, so now I'm good to go. So I'm going to do that number times 6 times 0.2, and that gives me 43.7532. So I'm going to do 2 sig figs here, because this is 2 sig figs, and that's going to give me 44 grams of hydrochloric acid solution. Easy. Don't complicate it. Doesn't have to be. Alright, so let's go back to our slideshow, because I think I'm done. I try to keep the videos light the day before you have a test, and so this one's a little short also, but then in the last video for the chapter, we'll talk about percent composition and how to calculate molecular and empirical formula. That video will be a little longer, but you got that chapter 2 8.1 test to concentrate on, so make sure that you do that.